Okay, so this video is for part B of the January 2025 Regents exam. This is video 2 of 2. 1 of 2 was the multiple choice. So we start off with number 34. We have a vector question here, and we want to know what's the magnitude of the resultant force if the vectors are at right angles to each other. So we know that if vectors are in the same direction, we add them up, we add their magnitudes. If they're in opposite direction, we subtract their magnitudes. But if they're at 90 degrees, like these guys right here, we use Pythagorean theorem. So I can do 20 newtons squared plus 40 newtons squared is equal to our resultant squared. And since 20 squared is 400 and 40 squared is 1600, adding them up gives us 2000. But r squared is equal to 2000, so r is radical 2000, or 48 newtons. So the magnitude of the resultant force is going to be 48 newtons. Now you could do this to scale. You could redraw the 20 Newton vector over here, kind of shift that guy over, and then the resultant goes from the starting point to the opposite corner. But I couldn't draw that to scale because I don't know what the scale is. You can kind of make a scale, but even on this video, I can change the scale just by pinching. So, yeah, if you have vectors at right angles, just go ahead with the Pythagorean theorem, and then you should be fine. Now it says, what is the angle of measure the angle in degrees between east and the resultant force? Well, this way is east, and this is the resultant force. So you don't actually have to draw the resultant. You could use tangent to figure this out. There's actually two ways of doing it. So I can show you that even no matter what the scale is, the angle is going to stay the same. So you could just use a protractor to figure out what that angle is. And so you should get somewhere around 27 degrees. If you were using a protractor, you get a wiggle room of 2 degrees. So if we were using a protractor, that would be anywhere from 25 degrees to 29 degrees. But that's 27. We say opposite over adjacent. This would be 20 newtons over here as the opposite side. The adjacent side is 40 newtons. And so if tangent of theta is a half, then second tan in your calculator, your TI calculator, second tan of a half in degree mode is 27 degrees. That's how I figured that out. So that is 34 and 35 for vector questions. Notice that both of those are one-pointers where the units are already given, so you just have to write the answers down. You don't have to show any work. For this guy over here, you do have to show work. So we have a 747 jet traveling at 70 meters per second north, touches down, then it slows to a stop at the rate of 2 meters per second squared. Let's write givens. So we have the initial velocity of 70 meters per second and then coming to a stop, and then it says it slows to rest at the rate of 2 meters per second squared. So I know the acceleration, meters per second squared, tells me that this is acceleration. But I'm going to make that negative because the plane is slowing down. If I'm going to call my initial velocity positive and the plane is slowing down, the acceleration is against the direction of motion, so we're going to call that negative. And now it wants to know how far did it go as it slowed down. I don't have the time. I'm not going to need the time. I can use the equation on page 6 of the ref tabs. Vf squared is Vi squared plus 2AD. And so my VF is 0. My V initial is squared. My V initial is 70. My acceleration is negative. Oops, I forgot the 2. Negative 2 meters per second squared, and I'm solving for D. All right, so that's 0. Let's see what 70 squared is. So I get that 70 squared is 4,900, so I have 0 equals 4,900 minus 4D. And so I want to get D by itself, so I subtract the 4,900 from both sides. I get negative 4,900 is equal to negative 4D, so I divide both sides by negative 4 to get rid of that. And I wind up with a displacement for our airplane of 1225 meters, and since all the numbers are 2 sig figs, the actual answer would be 1200 meters. But if you wrote 1225, you would be fine. Notice I listed everything with their units. I wrote the full equation here. Notice my full equation. And then my unit substitution in the next line, meters per second, meters per second, meters per second squared, right? I did not need to write, in this part here, I did not need to substitute with units, but I did include units with my answer, right? So you don't need to you don't need to show all this work and all this business for multiple choice, but for 2-point questions, you certainly do. All right. Okay. I'm wondering if my work is going to get cut off. Let me see what I can do here. There. I actually rewrote it so that it will actually show up show up and not get cut off on the page. I thought it was going to get cut off on the page. Let me actually make sure. Oh man, looks like this is going to get cut off on the page too. All right, let me try and fix that. There, now it shouldn't be cut off. So 34, 48 newtons, 35, 27 degrees. And then we have this guy here with our jet, 1200 meters for 2 significant figures. That was a kinematics problem. Okay, and then after kinematics, we have motion graphs with 37 through 39. 39 is over here. All right. So we have a graph, and so first thing we determine when it comes to graph is type of graph, and that graph is going to be a V versus T graph. All right, and so it says using information in the data table, construct a graph on the grid using the data points. Now, it's already scaled for you, so when they say construct a graph here, they mean they want you to plot. So the time is all laid out pretty well. For time 0, we have a velocity of 24, so I'm going to mark right there. Then time 1, we have 19, which is going to be right here. Then for 2 seconds, we have 14, just beneath 15 here. For 3 seconds, we have 10 seconds right here on the money. I'm sorry, meters per second, 10 meters per second. And then for 4 seconds, we have 4 meters per second, and that's going to be down here. And it looks like these are going to connect for a pretty straight line. And it says, draw the line of best fit for the data you plotted in number 37. This is looking pretty spanking linear. And that's my line of best fit. I wish I could make it a little bolder, but you can still see that it's there. So there is, oops, that didn't work. There. Okay. Why is it, my line is, what is my line doing? Ugh, I'm just going to freehand it. Got my handy dandy straight edge here, and so I drew myself a line of best fit. There it is. That one's bolder anyway. And it scales with the rest of the page. So that is the graph, that is the plot, choice 1. That is the line of best fit, choice, 1 point on 37, and then 1 point on 38. And then 39 says, using the graph, determine the acceleration of the car from a V versus T graph. V versus T, the acceleration is going to be the slope of the line. Or you could also just simply do A equals delta V over T, which is also the slope of the line. So I have to go back to the line to actually figure this out. So kind of rise over run. I can kind of use, let's see, pick some points here for my line of best fit. Now you can use data points for this only if those points are on the line. All right, so I have my 2 points, and so I'm going to do 3.8, or rather the delta y over delta x, 20 minus 5 over 3.8 minus 0.7. Notice I wrote an equation, a equals slope. I could even, delta v over t if I wanted to write that, or delta y over delta x, if I wanted to write that out. But I have 20 minus 5, that is 15, over 3.8 minus 0.7, which is going to be 2.9, and or roughly 3. I mean, this is going to be an approximate value, and so I have 15 divided by 2.9, make that 3.1. It's a little late making this video. I think this might be the last problem for this sit down. So 15 divided by 3.1, somewhere around 4.8 meters per second squared. There's going to be wiggle room for that answer based on the line that you drew over here, on this guy here. But, you know, and again, you could also use delta V over T, you know, whatever works. But you should get somewhere around 4.8 or 5 meters per second squared in that ballpark. Again, 2 points, so make sure that you have an equation and that you have substitution with units and that you have units with your answer. Okay, so for number 40, we have a kicked soccer ball at an angle of 40 degrees, and I'm not going to use a protractor, so 40 degrees is like roughly kind of like that. And it says, sketch the path of the ball's flight from initial position until it returns to level ground. I want it to be kind of like a parabola, so like parabola-ish curve. There it goes. And so there's the curve for a kicked ball. Any projectile at an angle really is going to have that curved shape, parabola. Okay, 41 and 42, we have a object on a frictionless surface. We know its mass. The mass is 5 kilograms. We know its weight. That's nice that they also told us what the weight is. We didn't have to calculate it. It sits on a frictionless horizontal surface. Horizontal pushing force towards the right is applied, so the F push is 20 newtons. And 41, once a vector drawing, it says use a scale. The scale of 1 centimeter equals 10 newtons. And it says draw the vector to represent each of the 3 forces acting on the block. And it says it's okay if your drawing vectors go into the wording of this problem. Yes, it would. All right, so we have weight. We also have the normal force from the ground on the block, which is also equal to 49 newtons. That's because of Newton's third law. And so we have 3 forces. We have the weight, we have the normal force, and we have the pushing force. The scale is 1 to 10, so we can just move the decimal place on these guys. You should use a straight edge. I don't have my ruler on me, so I'm going to do my best. So we have F push here, going to the right, and that would be 2 centimeters long. And then we're going to have the weight and the normal force. So there's my normal force, and there's my weight. That is approximately right. And then we're going to label them, normal force. You don't have to write the length of it. I'm writing that here. We have FG down here. That is also 4.9 centimeters. And those are the 3 vectors. And I kind of freehanded that. I think I did a good job, but use a metric ruler and straight edge, not just a straight edge, but you'll need the metric ruler in order to measure those vectors. Also, don't forget arrowheads. Just having a line is not enough. And then 42 says, what is the acceleration of the block? So I could use A is delta V over T, but I have no idea what the speeds are or the time, so that's not going to work. I could also use A is F net over the mass. And the normal force and the weight cancel each other out, so the net force is the pushing force. You could say net is push minus friction, and that there is no friction because it's a frictionless surface, so you would just wind up that with the net force is the pushing force. And we know what the pushing force is. We wrote that above. The pushing force was 20 newtons. So we have 20 newtons divided by the mass, which is 5 kilograms. And so we get 20 divided by 5. We get an acceleration of 4 meters per second squared. All right, 43 and 44. We have circular motion because the car is going in a circle. They tell us the mass of the car is 1.5 times 10 to the 3 kilograms. That's 1,500 kilograms. It's going at a constant speed of 12 meters per second, counterclockwise. All right, so notice the direction of the car's motion is counterclockwise around a circular track with a radius of 50 meters. And so then 43 says, on the diagram, draw an arrow to indicate the direction of the velocity of the car. So the velocity in the position shown. At the position shown. All right, so the car is right here. There's the car. And the velocity is always straight forwards. It's the force and the acceleration are inwards. So the FC or the F net are inwards. So is the acceleration also inwards because it's the direction of the velocity, direction of the force, sorry. But the velocity is always straight forwards. Now, the direction of the car's motion does matter. The fact that the car is going counterclockwise means that the velocity is to the left and not to the right. If it was clockwise, the velocity would be going the other way. All right. And then number 44 says, what is the centripetal acceleration? I know from page 6 of the ref tabs that centripetal acceleration is speed squared over the radius. We know the speed is 12 meters per second. Don't forget that sucker is squared over a radius of 50 meters. That gets me an acceleration of 144 over 50. And that gets us 2.88 meters per second squared for the centripetal acceleration of the car. Don't do delta V over t, because 1, that's not centripetal acceleration, and 2, it's constant speed at 12 meters per second. There is no delta V. So there's that. This is not looking like a C. There, that's better. Okay, that was 44. All right, we're getting close to the end. So we have more circles. 45 says a 1.5 kilogram cart travels in a circle of 2.4 meters at a speed of 4 meters per second. And it just wants, I could write down the given information, but 45 just wants an arrow. This is on the blank circle above. Draw an arrow to represent the direction of the acceleration of the cart in the position shown. And the centripetal acceleration is always inwards. All right, so that would be to the left for the position shown. It says label the arrow A. I labeled it AC. Good enough. All right, so that's 45. 46 and 47. And so things we know about 46 and 47, we have the mass is 1,200 kilograms for our car, and it's going east at 25 meters per second. The initial is 25 meters per second east, and it's brought to rest in 5 seconds. And then 46 wants to know the direction of the impulse applied. Well, impulse is F net t. It causes a change in momentum, which is mass times a change in velocity. But the impulse is the same direction as the force. So the car is traveling east, but it's slowing down, so the force opposes the motion. So the force would be west, and the impulse and the net force are in the same direction, so the impulse is also west. Okay. And then we have 47, once the actual impulse as you brought to rest. I'm going to say C number 46. I don't feel like writing the givens again, but it wants to know what is impulse. I don't know the amount of the force. I do know the time, but I don't know force, so I can't do FT. I don't know the momenta, so I can't do delta P, but I do know the mass and the two different velocities. So I have J equals M delta V. Now remember that the equals M delta V piece of that equation is not on the reference tables. Ref tables. And we need it here.
Oh my gosh, hey Reese, hey Lena.
And so we come to rest. It's 1,200 kilogram car. It started at 25 meters per second, so 1,200 times negative 25 is negative 30,000. and it's kilograms and meters per second. So you write kilogram meters per second, but you could also write Newton seconds. Those are also possible units for impulse. Okay, and our last two questions on the 2025 midterm. And so we have 48. We have a car going east, hit from behind, receives an impulse of 6,000 Newton seconds. What is the change in momentum? So let's write down the givens. 48, we have a 1,000 kilogram car going 50 meters per second east, hit from behind, receives a forward impulse of 6,000 Newton seconds. So forward impulse, that's in the direction of motion, 6,000 Newton seconds. So also east. And it wants to know, what is the change in momentum? Well, let's not forget that the change in momentum is the impulse. They are the same thing. So you could just straight up write 6,000 Newton seconds. You don't even have to write Newton seconds or kilogram meters per second. It's a 1-point question. The units are given. So you just write 6,000. Boom. All right. And then the last question, we have an explosion question for a cannon and a cannonball. So we have a cannon that's just chilling, and then it has a cannonball inside of it, and then boom, there goes the cannon, and cannon rolls backwards. And then the cannonball that just got blown out of it goes forwards. All right. And I wrote out all the info for the cannonball and the cannon. But in an explosion problem, the cannonball goes one way and the cannon goes the other. So it says that after being fired, the momentum of the ball is 2,400 kilogram meters per second east. So if the cannonball is going east, the recoil of the cannon must go the other way, has to go west. The other way. I don't have to do any calculations here. I mean, you can kind of, it's like, why is that? Like, justify that. So some of the momentum before equals some of the momentum after, but there's no motion before. So before the cannon fires, there's no momentum. So we wind up with P1 prime after is negative P2 prime in order for them to add up to 0. So the negative is the reason why the cannon rolls west if the cannonball is going east. And that's the last question for the part B of the 2025 midterm exam. All right. Thanks for listening. Good luck on your midterm.